Okay, my name is Jonah Flint, and this is my Physics 2211 Lab 5 report on the analysis of a slinky falling through the air. So as previously mentioned, the purpose of this lab is to analyze the motion of a slinky as it falls through the air and study the effects of gravity, tension, and drag as it does so. And then we are going to model the system in GlowScript as well as analyze the given video in Tracker. Some fundamental principles for this lab are Newton's second law and the derived velocity and position update formulas right here. And then we have the equation for the force of gravity and the equation for the force of drag. For our tracker model, we set the initial time to be 0 seconds, the initial y position, which is the only axis we care about in this case, to be negative 0.535 meters. The bottom of the slinky begins to fall at 0.267 seconds, and the slinky hits the ground finally at 0.417 seconds. And then I used Derek Muller's height as my reference, and he is 1.75 meters tall. And the origin, as you can see, is set to be the position at which the bottom of the slinky compresses to, and before it begins to fall as one whole slinky. In GlowScript, here we had to input the ball's mass. These are our initial conditions up here. The ball's position and velocity vector. I just found this in Tracker, and we're saying that it started with no velocity since it was dropped. Here we have our time and our frame rate, the force of, the acceleration due to gravity here, 9.8. And here we have our b value, which is used in the drag equation, and I found this just through trial and error. Here it is, as previously mentioned, 0.267 is the time to full compression of the slinky. And here we have our forces. In this case, this is just the first half of the system where the slinky is compressing. So we have the spring force right here, and we set that equal to the force of gravity. And in this case, notably, these two forces are equal and opposite, so there is no net force in this section of the system. And down here we have the position and velocity update formulas. In the second half of the system, where the slinky is fully compressed and the system begins to fall down to Earth, that happens at a time greater than 0.417 seconds, as previously mentioned. And notably, down here in the forces section, these two forces are no longer equal to each other, so there is a net force pointing downwards in this case. And again, we have the position and velocity update formulas. For our results, as you can see, there's a pretty similar shape from the GlowScript model or to the Tracker model, I should say. And this makes sense as we're modeling the same system with the same forces. And notably, as you can see in this section here and here, this is modeling the bottom of the slinky. And notice that it stays constant, or in a constant y position for about the same period. And this is because, again, as previously mentioned, there's no net force on the system at this time. The spring force and the gravitational force cancel out. So there is no net force and therefore no acceleration downwards. And then in the curved section, this is when the only two forces acting on the system are the forces of drag and the force of gravity. So this is why there is a net force acting on this time, and hence there is an acceleration downwards. Some of this rickety behavior here is error likely due to my inputting Tracker. This is just because the quality video wasn't fantastic, so there was some error in tracking the actual motion, and there's possibly some other human error in the video's creation itself and some inconsistencies in error resistance. All right, thank you very much.